Any questions you'd like to look at in particular today regarding what we were doing? Actually, some of the more important material of the course, actually. Okay, well, I'll remind you a little bit what we were doing. Screen here. You can see when I go off the screen. We had last time some important identities that came out of the unit circle, right? If we put an angle in standard position, here's an angle theta in standard position because its initial ray is along the positive x-axis and counterclockwise is positive. We had from this, by dropping this perpendicular and making a triangle, saying that x coordinate, x length is cosine x and the y length is sine x, so the coordinate of the point of the intersection is cosine sine. And the unit circle means it has radius 1. We found immediately that sine of x squared, which we wrote this way, plus cosine of x quantity squared, which we write this way, is equal to 1. Hopefully that looks familiar. That's one of the most fundamental identities of trigonometry. If we divided this through by the sine squared, what did we get? Well, sine squared over sine squared was 1. Cosine squared over sine squared turned out to be cotangent squared. We're going to show more plainly why that is this time. But cosine, if we divide it, you can imagine it. I don't know. I hate to reprove it. But you divide the whole thing through by sine squared, so this becomes cosine squared over sine squared. But cosine is x and sine is y, so it's x over y squared is cotangent squared. This one becomes 1 over cosine squared, which is also secant squared. So without going through the proofs again, if you want, I'll do some of these. You just divide this through by cosine squared or sine squared, and you get this. And when you divide it through by cosine squared over cosine squared is, I should call this theta, sorry. Otherwise, I'll get it mixed up with the x and y here. Theta, because I call this theta here, not x. Just to be consistent. Divide through by cosine squared, and sine squared over cosine squared, we're going to mention again. Turns out to be tangent squared. Cosine squared over cosine squared is 1, and 1 over sine. Wrote this is cosecant squared. And 1 over cosine squared is secant squared. Sorry about this. These are the 3 Pythagorean identities. Divide this one through by sine squared to get this one. Divide this one through by cosine squared to get this one. We also had the reciprocal identities that the cosecant of any angle is 1 over the sine. And the sine correspondingly is 1 over the cosecant, which is over the sine. The secant is 1 over the cosine. Consequently, the cosine is also 1 over the secant. The cotangent is 1 over the tangent. And consequently, tangent is also 1 over the cotangent. We call them identities because these things are all true whenever everything's defined. Sometimes cosecant might be undefined and sine is equal to 0. That's okay. It's just whenever everything's defined, the two are equal. So we call these the reciprocal identities because they show which trig functions are reciprocals of each other. We call these the Pythagorean identities because they come out of the Pythagorean theorem for this triangle. Those look familiar, I hope. Been a while, but hopefully that looks familiar. So the idea is we have the unit circle, and when you take an angle in standard position, whatever position it intersects here, x, y, the coordinates are, the number x is defined to be the cosine of the angle, and the number y is defined to be the sine of the angle. That makes in this triangle, this cosine x, this sine x makes this true by the Pythagorean theorem. This squared plus this squared equals 1 squared. Where again, sine squared theta means take the sine of the angle and then square it. It's just notation, right? Definition or notation. And similarly with the other squares. And all these things came out of there. Now we want to expand these. Here's a real obvious one. The tangent of theta, could have used it here to prove this quicker. Sine of theta divided by the cosine of theta. How do we know that? Was there a question? Is that somebody's phone? Anyway, online you can go ahead and voice in if you just take your mute off for a second and put it back on, or you keep coming up on the camera all the time. I guess I didn't hear it from this room. All right, so this is true, and here's the proof. I like to do the proofs when they're short and insightful, and that's exactly what this is. The tangent of theta is defined to be the y coordinate over the x coordinate, right? That's what we said in the unit circle. Sine theta is y, cosine theta is x. But wait a minute, y is sine theta, x is cosine theta. There it is. There's one step in the middle, and you've got the proof, right? So this is easy to remember, right? Just think of the picture. Similarly, the cotangent of theta is the cosine divided by the sine, and these are extensively important, extremely important also, just like these are. And the proof, we'll call these proofs. The proof of this one is that cotangent of theta is defined to be x over y, but x is cosine and y is sine. So see, these you can figure out when you forget. Unlike all my Spanish words that when I forgot, I couldn't figure out. So, in some sense, mathematics can be easier to figure things out. These here, because they're quotients, we'll call the quotient identity. So I'll refer to these names occasionally, and the book will too. I should know what we're talking about, right? And now you can see this one a little more plainly. We proved it just using x and y last time, but you see how I proved this one? This one everybody remembers, right? Because you get the triangle. How do you prove this one? I just said it, but I want to prove this one from this one. And you take this one and divide it through by sine squared, right? Divide the whole thing through by cosine squared. That means I need to divide each term by cosine squared. Terms are things that are added together. So this divides the whole left by cosine squared. And now what's this? Sine squared over cosine squared, but that's tangent squared. Cosine squared over cosine squared is 1. 1 over cosine squared, well, 1 over cosine is secant. This is secant squared. So I just divide this by cosine squared, I get this one. Similarly, if I divide this by sine squared, we can do it if you want to get this one. That's why the book on this one puts 1 plus cotangent squared equals cosecant squared, but this one puts the other order, tangent squared plus 1. It's because this is the natural way to remember the proofs. Right? You divide through by cosine squared, you get this one. Divide through by sine squared, you get that one. So I like to put that in because I had more trouble remembering it. All right, so here's our list of trig identities so far, and I have one more. Recall that from the theory of algebra, you always wondered what you were going to do with this. F of x, a general generic function, is said to be even with what? What is an even function? Nobody knows what to do with this from algebra. So it's in there for this class and some of your subsequent classes, primarily this class. If f of minus x is equal to f of x. minus goes away. Or it can be, or it is odd if, let's ring a bell to know what odd is. F of minus x is, yeah, there you go, minus f of x, the minus comes out. So odd means the minus comes out, even means the minus goes away. So what that means about the graphs, like here's an even graph, y equals x squared, the minus goes away. If I graph y or f of x equals x squared, it's an even function because f of minus x is, put in minus x for x, you get minus x squared. But minus x times minus x is x times x is x squared, right? F of minus x is plus x. The parabola y equals x squared is an even function. But you can see what that does if you take any point here, x naught, find f of x naught, right? That's equal to f at minus x naught. So if you go over here, the same distance the other side, f of minus x naught has to be the same height. And so you get this symmetry. The point over here and the point over here have the same y value if you go out the same distance this way. So f of x equals f of minus x equals f of x means you have a symmetry across the y-axis. You get the same y value for plus x0 and minus x0. So that's even. It's some symmetry across the y-axis. That's the graphic characteristic. We need that for this class. Function is even means this, and graphically this means that you can flip it over the y-axis, it lands on itself. I should notice what it look like. It doesn't look like it lands right on itself when you flip it over here. Now, what does odd mean? Anybody remember that one? That means it has a symmetry through the origin. Because if you take x naught, there's some point here, f of x naught, this might be the function f of x equals x cubed. It's an odd function. But x cubed looks like it goes up like this on the right, but then it goes down the same on the left. And so if you have any point x naught here at minus x naught, f of minus, put x naught for x, the y value is minus value at what it was x naught. So this is minus x naught, which is minus the y value of this one. What happens now is you have this point the same distance down as this one is up, and now you've got a symmetry like this for the origin, the same distance the other side straight through the origin. So that's the characteristic. An odd function has symmetry through the origin graphically. Even function has symmetry across the y-axis, just by its definition. Okay? Now, every trig function is either even or odd. How about that? Wherever it's defined. And the trig functions, all 6 of them, are either even or odd. I should point out that most functions are neither even or odd, right? If I put y equals x squared plus x cubed, for instance, that looks like, I think something like this. Right, it's not symmetric across the y-axis or through the origin. So most of them are neither. However, all 6 trig functions are either even or odd. Right, so that's just to point out. These are a very important class of functions. They have these nice graphical properties. The trig functions satisfy. We can use the unit circle to prove it. The sine of minus theta is equal to minus the sine of theta. So is this even or odd? Yeah, odd. Just think of sine as f. The minus came out, right? How do I prove that, do you think? The unit circle. You can make a picture on here. I'm trying to leave room for all these. But here's the picture for sine. If you take an angle theta, drop the perpendicular, the y-coordinate is sine theta, right? That's the definition. Now I take an angle minus theta. That means I have to turn the same amount the opposite direction. So I drop the perpendicular, it's going to be the same length because I turned the same angle, but it's going to be negative. So this is the sine of minus theta, but it's the negative of this y-coordinate. There it is. All right. Sine of minus theta is minus sine of theta because I turned the same distance and got the same triangle. That's the outline of the proof. I think that's the way to remember it. So that shows you the sine of minus theta is minus sine of theta. How about cosine of minus theta? So I take a negative angle like this. What's the cosine? I drop a perpendicular and I take the x-coordinate. It's this. The x-coordinate is still positive because I turn the same amount this way as if I took plus theta, the counterclockwise angle. It'll be the same x-coordinates on this one, right? In both cases, this is cosine theta. It's cosine theta for the theta, and then when I take minus theta here and drop a perpendicular, it's also cosine of minus theta. So they must be equal, right? The same x-coordinate in both these triangles. So we find from for the cosine of minus theta is cosine of plus theta. It's even. How about tangent? The rest of these we can do actually without this. So these will be proofs over here. Is this big enough? Do I need to draw this bigger? I've ran out of room. Maybe a little bigger. Let me draw it down my corner. This works for bigger angles, but it's easiest to see in the first quadrant. Here's theta. The y-coordinate is sine theta. Here's minus theta. Turn the same amount, but negative. As you turn the same amount, it drops to the same point here. Well, since for this angle minus theta, the y-coordinate is sine, so this y-coordinate is sine of minus theta. But you notice it's the negative of this y-coordinate, sine plus theta. So you get the sine minus theta is the negative of the y-coordinate here. But they have the same x-coordinate. Doesn't matter if you went this way or this way, they drop to the same x-coordinate. So cosine of this angle minus theta is cosine of this angle, cosine plus theta, same x-coordinate. So that's the proof off the unit circle. Now the rest of them we can do another way. We said a tangent of minus theta, the minus also comes out. Part of the reason I do these is so that when you figure them out, or when you forget them, you can figure them out. It's easy going plus or minus, plus or minus, plus or minus. You ever see that old Danny Kaye movie from the 1930s? Jester in the King's Court. And he's nobody's seen that. It's too old. It was a classic. He was the biggest actor of his time, right, for a while. And you can see that one scene. You can Google that one scene, and he's the knight in the king's court, and they're trying to kill him, but he's a comedian. And he's got this poem somebody's given because he's going up against this other knight, and they're supposed to drink out of a chalice. Each one of them has a drink, and one of them's poison. And there's a poem he memorizes, so he can figure out which one has the poison in it. And he's trying to go over the poem as he's going up to take the drink, but the other knight also was given a tip and knows which one it is, and they, I'm confused trying to recite the poem at the same time. Nobody knows which one has the poison in it. That can be like this too. You don't know which one has the minus in it anymore because they all have minuses, and it's very confusing. But if you just, remember sine is odd and cosine is even, you can figure all the rest of them out. Here's an easy way to do it. One of the theorems from algebra says if you take an even divided by an odd, or an odd divided by an even, it's again odd. It holds in general, but let's show it here. Tangent of minus theta, this is the proof for tangent. Well, sine of any angle, or excuse me, the tangent of any angle, we just showed over here is the sine divided by the cosine of the same angle. So if I take tangent of minus theta, that's the sine of minus theta divided by the cosine of minus theta. Doesn't matter what angle, I just put it in both of these by the quotient identity. Now the sine, you see what? Sine, the minus comes out, you get minus sine theta. Look at my cosine, the minus goes away because it's even, you get cosine of theta. You get a minus on the top and 9 on the bottom because this is an odd one, this is an even one. And now that's minus sine over cosine, that's minus the tangent. There's the proof that tangent is odd. You use the even and odd properties of sine and cosine. This holds for even and odd functions in general. If you get f, the function f is a quotient of an odd and an even, it always comes out, the minus comes out of the odd and not out of the even. Odd function. And there were some other properties. That sounds familiar. Odd times even is also odd. Odd times odd is even, even times even is even. You see it on all these things. Cotangent of minus theta is minus the cotangent. It's odd. You do a similar proof. You just write cosine over sine, and the minus comes out the bottom this time. Secant of minus theta. The minus goes away. It's even. Maybe I should do the proof of that one if we're good enough room here. Secant of minus theta. Here's how you prove this one. Well, secant is 1 over cosine of whatever angle you put in, right? So it's the cosine of 1 over the cosine of minus theta. But cosine is even. Right? So once you know these two, you know all. But if the minus goes away, you get 1 over cosine, but 1 over cosine is secant. That proves that secant of minus theta is secant of plus theta, and the minus goes away by definition, right? It's even. And then correspondingly, the cosecant being 1 over the sine with a similar proof, the minus comes out. So there's the 6 even odd identities. Every trig function is either odd or even. Unlike general functions, both of them can have to be. If you can figure these two from the unit circle and the others follow. So I did cosecant and cotangent. I didn't do those two. I don't know if you want to do those. I just ran out of room, so I didn't. Sometimes it's worth doing them all once. Cotangent minus theta. Cotangent is cosine over sine, right? Of whatever angle you put in. So it's cosine of minus theta over sine of minus theta. Sine is odd, the minus comes out. Cosine is even, the minus goes away. But minus on top or bottom is the same. Minus cosine over sine. Oh, that's minus cotangent. That proves cotangent is odd, right? The cosecant of minus an angle 1 over the sine by the reciprocal identity. On the sine, the minus comes out. Minus 1 over sine theta is minus cosecant theta. Actually, proof cosecant is odd. The odd thing that comes out of this, you might think half of them will be even, half will be odd, right? After all, they're just x, y reciprocals. No, 4 of them come out to be odd and 2 of them come out to be even. That always makes it confusing. The way I keep track of it, when I can always prove if I have to, but it's easier for me to think cosine and its reciprocal are even. All the others are odd. That's my way. You can do it whatever way you want. But you want to know these even odd identities. Those are the identities we need to know for now. There will be more identities as we go along. These are the most important ones of the course, probably. Questions online and all right. I want to do some review problems using these ideas. Because some of these are hard and you won't do all of these. Uh, suppose tangent theta equal to 4, and the terminal side of theta is in quadrant 4. I'll write this way. What is the secant of theta? About that. This is the hardest one, actually. What I call the different cases, because I'm going to give these to you in your first exam, which, by the way, is coming up in 9 days. So be studying. I put the review problems practice exam out on the web. Don't be scared by its length. The actual exam will be shorter. It's supposed to review the major concepts clear through. It doesn't review everything for the test. The homework is assigning is a review of everything for the test, but it will hit most of the major concepts. If you can get all those right, you can pass it. Hey, you got to do all the homework, right? That's the way it works usually. Anyway, the practice problems are out there. They will give you the flavor of exam problems. They're old exam questions that I put into a practice test that's probably 3 times as long as the real test. And some of them are like this. They'll say, given a trig function and a quadrant, find another trig function. Remember, this is one of the 3 cases where you find all the trig functions. What do we then find all 6 trig functions? Given a value of 1 trig function angle, right? If we're given a point on the terminal ray, right? Or if we're given a special angle, those 3 cases at least, we can do all 6 trig functions. Right? Special angles, trig function, and a quadrant, or a point on the terminal ray. We can always figure all 6 trig functions. So I'm going to do that here. Take trig function and a quadrant. What can I do? What I do, when I have the identities, we have more ways to do it. Before we said you could do this using the unit circle. Now you can also do this using trig identities. So it's a review problem, but it's also going to, in fact, I use some more trig identities. If I have tangent theta equals 4 given, well, yeah, if we just go back to the unit circle, right? We said one way you can do this in the unit circle is to say, well, this looks like 4/1, right? Maybe since tangent is sine over cosine, sine is 4 and cosine is 1. That's not possible. Why not? This is weird. Tangent can't be 4. I read this off of here. Hold on. Tangent is negative in quadrant 4.
Tangent's positive in quadrant 3.
Yeah, it's just a problem. I'm reading this. I don't remember any error on this problem. Well, in quadrant 3. Yeah, tangent is negative in quadrant 4. And I was on the committee to help put these together years ago. But we got all the errors out of these. All right. There are some errors you knew about it here. Suppose it's in quadrant 3. Tangent will be. This can't be the sine and the cosine within the quotient there, because this is a point on the unit circle. You got a terminal ray over here, quadrant 3, and theta could be this angle. But if they both be positive, say, oh, I know it's -4 or -4. No, that's way out here. This is only one in the top. What you have to do is rewrite it. Right tangent as a quotient, and then divide the top and bottom by the roots of the square. 4 squared plus 1 squared. There are other ways to do this. I'll show you part of what I'm saying with the triidentity in new ways is the square root of 17. Both these triangles come out with nasty numbers. I gave you some nice 3, 4, 5, and 5, 12, 13 triangles. Most of the time, triangles come out with nasty square roots for their side lines. So this one, when we make the triangle, we're going to have a square root of 17. But you compute your right tangent as a quotient, then you root sum square the number of those quotients. You could also use 8/2 or 40/10, whatever you want, and do root sum square those. It doesn't matter. I just pick the easiest numbers. These ratio is 4. Now you rewrite tangent by dividing each of these by the root sum square. So 4 over square root 17 and 1 over square root 17. And this will be a point on the unit circle. You take this squared plus this squared, it will be equal to 1, which makes it on the unit circle. Alas, it's up here. It's y equals 4 over square root 17. I won't bother to rationalize it here. X equals 1 over square root 17. But that's a point in quadrant 1 whose tangent is 4. So what am I missing? Well, you could also take minus this. You can also divide by minus square root 17. So there's two choices. You can divide by the root sum square of these numbers or minus these numbers. And this one is not what you want because it's in quadrant 1. This one is because it's in quadrant 3. What's the point? Minus 1 over square root 17 x. My tangent is y over x. So this could be the x coordinate, and this could be the y coordinate. And it would have the right tangent. And this could be the x and this the y, and it would have the right tangent. We also specify we want quadrant 3, then it's got to be this one. That's the only point. Well, once we've got the point coordinates, we've got everything, right? Because x and y determine all 6 trig functions. So now, for instance, secant theta. I don't even know what the angle is, right? I just know what its tangent is. Secant theta must be 1 over the x coordinate. Is 1 over minus 1 over square root 17. Well, the reciprocal is the number back. You get minus square root 7. So there it is. The secant of this angle, whatever it is negative square root 17. So, but this is the method we used last time. And I'm telling you, this is actually the hardest case. If this one seems really hard, it is. Sine and cosine are easier. If I give you the sine, you know the x coordinate immediately, you can find the y coordinate, right? But if I give you the tangent, you go to this thing, you got to write it as a quotient, take the root sum square. This is one way to do it. However, there are other ways to do it now that we have our trig identity. What would be another way to find secant? Oh, awesome. Yeah. Alternatively, sometimes it's easier to use an identity. You can use whichever you want in the test. Since this one, tangent squared plus 1 equals secant squared, I can solve for secant in terms of tangent by square rooting. I got the secant theta. So this is Pythagorean identity. I can square root both sides, and I have to put plus or minus here. Why? Yeah, there's two solutions, right? If I put x squared equals 4, and a number squared equals 4, x could be plus or minus the square root. Right? This radical means the non-negative number that has square 4 means 2. So plus or minus 2 are both solutions. Same thing here, plus or minus the number whose square is tangent squared plus 1. So we said that last time. So secant is plus or minus this, but tangent was 4. Well, wait a minute, do I want plus or minus? I want minus. What you recall is that in each quadrant, all 4 trig functions have one sign. If I take an angle theta in quadrant 4, it doesn't matter if I draw it in the right spot. Here it is. On the unit circle, the x coordinate will be negative. So secant theta being 1 over x will be positive over negative. So you can figure it out. I don't memorize, trig function. Secant is positive here and negative here and all that. I just figure out which quadrant it's in and say, secant has the same sign as x plus or minus, and x is negative over here. All right, so I want the minus for quadrant 3. And so secant theta reversing side is minus the square root of tangent squared, 4 squared, plus 1 is minus the square. Isn't that easier? I didn't have to remember all that finagling. So depending which function you're trying to find, maybe it comes up in one of those nice quotient identities, right? And you save yourself some time. If you remember tangent goes with secant, the Pythagorean identity, you do it that way. Instead of doing this unit circle stuff. So there's I should call it the exercise. Right. This is the most fundamental one. Suppose sine theta equals minus a half. Cosine theta equals square root of 3 over 2. What is tangent theta? Here's what we did last time. We did the unit circle. We said you can put sine theta is the x, is the y coordinate, excuse me, and cosine theta is the x coordinate. So we go up to this point 1/2 square root 3 over 2 is close to 1. Here. There's the x and y coordinates. And we say, oh, tangent theta, y over x, y is 1/2. X is square root 3 over 2. Did I say quadrant 1? Oh, it doesn't matter. Yeah. Actually, this problem is minus a half. I'll change the problem from the homework. This x is square root 3 over 2. And now the 2's cancel since they're both denominators. And I get 1 over square root 3, which is a good answer. Or if you want to rationalize it, match the answer on the back and see if you're right. You multiply top and bottom by square root 3. Either one of those. What's an easier way to do that? Now that we have identity. Tangent is just sine over cosine. So easier would be to use the quotient identity. If you know sine and cosine, you immediately know tangent. Alternatively, by the quotient identity, tangent sine over cosine is immediately 1/2 over square root of 3/2. Cancel these is 1 over square root. Or rationalize it. We have to draw the picture again. Some of these problems are just these proofs I gave you. I did them all, but I'll repeat one, right? So, for instance, that secant theta, how do I show that secant theta is even? I just go back to the definition. I tried taking secant minus theta. Quotient identity, that's 1 over cosine of minus theta. But cosine is even. This assumes that you knew cosine was even. 1 over cosine theta is secant theta. So I'll say given sine is odd, cosine theta is even, which you can prove on the unit circle. We did it. But assuming you know this is odd and this is even, the rest, the other 4, just like this, I think it's best to memorize. So I'll let you assume that that's true. Just write this. Secant minus theta, secant theta is definition of even, right?
Mr. Stapleton,
Yeah.
we can't see online what you're doing.
I'm sorry. Thank you. I keep forgetting to do that. Yeah. So if you get this one, tangent is sine over cosine. I can just write 1/2 over square root of 3/2 and cancel the 2's. So the quotient identity is an easier way than using the unit circle. And secant theta is easy to show it's even once you know sine is odd and cosine is even. You just memorize those 2 from the unit circle. And then secant of minus theta is 1 over cosine of minus theta is 1 over cosine theta because cosine is even. But that's secant. Thank you, by the way. Well, I have one last set of identities actually to do here. And then we'll be done with identities for a while. Called the cofunction identities. So I think I'll do them in 1 second here. Yeah, because they're in the next section. Let me do this first. I'm sorry. Application to right triangles. Keep saying these things are really important right now, but there's a lot of stuff that's absolutely fundamental trig. One of them is the application of these trig functions to right triangles. And so this is extremely important, but it's also fairly straightforward. It's not like it's real hard. These trig functions are used to solve right triangles a lot. Given like an angle and a side and an angle, or 3 sides, this kind of thing, you can solve triangles. Application to right triangles will say this. Any right triangle it turns out that the sine of the angle is equal to the length of the opposite side. I'll just write opposite, meaning the length of the opposite side, divided by the length of the hypotenuse. Here's the picture. Let's put theta in this corner. You can put it in either one. Typically, people put it down here. The opposite side means the side that's not used to form the angle. The adjacent side is the leg that is used to form the angle. And the hypotenuse is the side opposite the right angle. So I go back to the first day. Opposite leg doesn't help form the angle. The adjacent leg is the one that does help form the angle. Hypotenuse, side opposite the right angle. All right, so the sine is just the ratio of this side to this side. What's the proof of that? Can you guess? It's pretty easy. Unit circle again. Here's why. Am I still on? Yes. Draw the unit circle. Put the angle in standard position. Put it in the first quadrant just for convenience, but this works in any quadrant. Well, actually, I said for convenience. Any right triangle has to be in the first quadrant. So this, right? These two angles are both acute. This is 90, so these add up to 90. They're both less than 90. They have to be in the first quadrant. So in a right triangle, the angle is always in the first quadrant. And what you do is you form this right triangle with that angle theta that's in your triangle. Now, your real triangle is not this size, probably, unless it's hypotenuse 1, that's not it. Your triangle looks like this, right? Some bigger or smaller size, but with the same angle, theta. Now, if you take the opposite side to the hypotenuse, what's that? By similar triangles, it's the same ratio as y to 1 in the right triangle, right? By similar triangles, y is to 1 as opposite is to hypotenuse. There it is. Y is to 1, right? The sine of theta is y, by definition, is y over 1, is by similar triangles, opposite over hypotenuse. That's the proof, right? The cosine theta is the x-coordinate by definition. Well, that's x over 1. That's the x over 1 of little triangle is to adjacent over hypotenuse in the big triangle. So now in any right triangle, I've just proved by similar triangles that the cosine of theta is the length of the adjacent side divided by the length of the hypotenuse. This is the foundation for solving right triangles, is that every right triangle is similar to a right triangle in the first quadrant, and you can use our unit circle then to figure the sine and cosine and all the other trig functions. Tangent theta, well, tangent is y over x, and by similarity, that's opposite over adjacent, right? And now comes the easy part, right? The last three are reciprocals of the first three, right? You just turn these all upside down. So once you got these, you're home. Cotangent theta, I turn this one upside down. I get adjacent over opposite. Secant theta, I turn the cosine theta upside down. I get hypotenuse over adjacent. And cosecant, I turn the first one, the sine upside down, and get hypotenuse over opposite. These are absolutely foundational to solving right triangles. These 6 triangle ratios. Now, see, the idea was you could tabulate, and put in tables, trig functions for all sorts of angles by using the unit circle and Pythagorean theorem and calculating square roots. And you get a whole table of trig functions for each angle. You know, if you put in 1 degree, this is the sine, right? Like using I put in 2 degrees, this is the sine. And if you went down to bookstores when I was young, at least, you could find books that were this thick, tables of 5-place, you've seen them. 5-place trigonometric functions. Don't buy them because all it does is show you what your calculator would get if you put it in your calculator, right? You can still find those once in a while. Don't buy it. It's better to have a calculator than a thick book, right? But that was the idea, is that by similarity, once you could know ratio size of a triangle on one side, you could look up in the book what the ratio is supposed to be from the unit circle and figure out how to solve the triangle. So here's what we get now, that we can do now that we have this set of relationships for right triangles. We can solve right triangles, believe it or not. Using a calculator that takes the place of all those ones that people figure out painstakingly with square roots of the mistake. In those special cases where we know a point on the terminal ray, or we know it's a special angle, right? Or we know one trig function at 5, and we can figure out exactly the trig functions. But in practice, we may have to use a calculator for all the other ones, right? Whether we get an exact angle figured by hand or exact value of the trig function, we can now solve right triangles. And here's an example. Let's put 1. Given a side and an angle of a right triangle, we can solve the triangle. We can find all the angles and sides. We do this, we find another side using one of these trig relationships, guard. Find another side. Well, let's do this first. Find the remaining angle by the sum of angles theorem. PHM for theorem. We can then find another side by a trig relationship. Any one of those. And then C, we can use the Pythagorean theorem or another one of these. Usually easiest to use the Pythagorean theorem. To find the last side, and then the triangle's solved. And this always works. If you're given an angle on the side of the right triangle, you do this, you find the last angle by the sum of angles theorem. Sum of angles is 180 degrees, or something easier. In a right triangle, the sum of the two non-right angles is 90 degrees. Remember, they're complementary. And then use a trig relation, use the Pythagorean theorem. Let me see if I can do this then. I think I've got enough room. Suppose I'm given that, this triangle, this angle is 30 degrees. And this side length is 7. And I said, solve this triangle. What are all the other angles? It's a right triangle. Solve that one. An angle and a side in a right triangle, I got it. What I can do is this immediately. I think it's easiest to use the complementary angle theorem and say that if I call this, I can label these. I could call this B and call this C. And if this is B, then this has to be called beta by our convention. And then this is alpha. And this is A. So I can use labeling A, B, and C is always the hypotenuse in the right. And then beta goes opposite B, alpha goes opposite A. Solve this. First thing I do, part A, is find the complementary angle. I know that beta is 90 minus. I'm given, must be 60 degrees. This is a 30, 60, 90 triangle. And these two angles always add up to 90, so that with the right angle, they add up to 180. So these are always complementary. One's 90 minus. Now I use a trig relationship, and I say, well, by trigonometry, I use a relation giving two numbers I know and one I don't. Maybe I want to find C. So I'll use these two numbers I know together with C. How can I use those in a right triangle? I'll say, well, opposite hypotenuse sine of this angle is this over this. Sine of 30 degrees is 7 over C by equation star trigonometry. Now I just take reciprocals and say, oh, therefore, 1 over sine 30 degrees is C over 7. At this point, it's algebra. You can solve it any way you want. You can cross multiply. Maybe that's the easiest way. That's the easiest way to do it. Let's just cross multiply. Now, stop. All right. So now you multiply by 7. So these are equivalent by division. Divide both sides by, or take reciprocals of both sides. And then multiply by 7, and you get 7 over sine theta. 7 over sine 30 degrees equals C. Well, we're lucky here because this is a special angle. What's the sine? Yeah, it's just equal to a half. We have memorized already this triangle here, 60, 30, 90, and 1/2 goes opposite the 30-degree angle, and this is square root 3 over 2. So we can say sine 30 degrees is opposite of our hypotenuse is a half over 1 to half. From the triangle we memorized. Or we can put it in the unit circle. So we get this one exactly. So we have here that C equals 7 divided by a half. Well, that's the same thing as 7 times the reciprocal of half. 7 times 2 is 14. I got the side length, 7, 14. And I've got both angles. I'm just missing B. So how do I get B? I can use a trig relation again, relating two numbers I know and B that I don't know. But what's usually easier people like to do is use the Pythagorean theorem for the last step. So the last step, I'll just say part C. By the Pythagorean theorem, solve for B. B is the square root of hypotenuse squared minus the other leg squared. Pythagorean theorem. So let's see, that's 198 is it? Square root of 6 minus 49. 140, square root of 147. So there is the two sides. This one can reduce, right? You don't want to put that on the test. What's wrong with that? Yeah, so I can pull,
Seven.
let's see.
It's 49 times 3, so we can pull out 7.
Yeah, it's 7 times square root 3, yeah. And this points out something interesting. You could actually solve this with similar triangles. You could say, oh, this triangle, being a 30, 60, 90 is similar to this one. The short side is 14 times as long, so this one has to be 14 times 1, and this one has to be 14 times square root 3 over 2 is 7 square root 3. You could have done that with similar triangles, right? But that's the whole point here. You can not only do this for the two triangles we memorized, there's one of the two special triangles. You can do this for any right triangle now. It doesn't just have to be those special cases. We can similarly scale up anything. Suppose I gave you this one. Suppose I give you this triangle, and it's a long one here. Suppose this side is 12. And this angle is 10 degrees. This is on the homework. 4p. And I said, solve this right triangle. This one is not a special triangle. I can't just scale it up like that. I have to use these 3 steps. So now we have those 3 steps as an alternative to solving the 2 triangles we know. But moreover, we can solve any right triangle by basically using similar triangles to the one that's in the circle. What you do is step A, if you already know one angle, you find the other one by subtracting from 90, right? If you call this beta and this B and this A and this C, that's alpha, like before. We'll say beta is 90 minus the angle you do know is 80 degrees. So I know the last angle. Right? One side I can find by trigonometry, the things I just related. I need to put in 2 numbers that I'm given and one that I'm not, and compare it to one that I don't know. So I need to use this angle on this side. I can compare any side I want. Why don't we do B this time? We'll say the cosine of this angle is the adjacent side of the hypotenuse, right? The side that helps form the angle divided by the length of the hypotenuse. So let's say cosine of 10 degrees by star. Cosine is adjacent over hypotenuse. Is B over 12, right? And now I'll just multiply by 12. I've got B equals 12 cosine 10 degrees. Now it's not a special triangle, so I can't just figure it by hand like I did last time. It's not a special angle, but I can figure it on the calculator. So I'll take on the calculator, you have to make sure you're in degrees mode. It can be in radians mode, and you put in cosine 10, it'll give you cosine of 10 radians, right? So it has to be in degrees mode. Let's see if it is. Push the mode button. Oops. Perfect. Just at the moment I need it. So while you get it, work a few more times with pulling the batteries out for a second. Probably won't work, but we'll try. I have another calculator in my office. Okay. Cosine of 10 degrees. Make sure it's in degrees mode. Oh, when I push mode, it goes on.
You want to borrow mine?
Okay, thank you. Yeah, so this one says it's in radians mode, so I'll switch it. Okay, now it's in degrees mode. And cosine of 10 is .984807753 to a whole bunch of digits. If you multiply these and round, so I'll multiply that by 12, I get about 11.818. The 3 decimal places. Then when you're done, you should always do sort of a sanity check and say, does that make sense? Hypotenuse always has to be the longest side, so if I get something bigger than 12, it's wrong. This is really close to 12, is that okay? Yeah, that's okay, because this is a really tiny angle. This one should be almost as long as, well, it looks reasonable, right? This should be mostly as long as this one, but less. Now I get the last side. I'll simply say in part C, and I'm left with A, so A is the square root of the hypotenuse squared, which is 12 squared, minus this side squared, 11.88 squared, which is approximately, if I round it off, I get about 2.082. This one should be small because it's opposite a really small angle, so that looks right too. If these are way off, it's probably because you have your calculator in radians. So the calculator says you can do all these things here. The question is, well, given an angle on the side of any right triangle, you can solve the right triangle. One more case you can do. I don't know if I have enough time to finish. I hit this. Also, given sides of a right triangle, we can solve the right triangle. How can we solve that one? That method. We know two sides of a right triangle, we can. This time we can immediately apply the Pythagorean theorem to find the third side, right? Because it applies to right triangles. To find the third side by Pythagorean theorem, you also use trigonometry later, but this is the easiest. Now you've got two angles left to find, right? You've given two sides, you just found the third one by Pythagorean theorem, you don't have any angles. So what you do is you use inverse trigonometry. To find one angle. There's an inverse trig button on your calculator that tells you what angle has that sine or cosine or whatever it is. It's up above the regular trig function. I'll do that in an example. I don't know what you. And then use the sum of angles theorem to find the last angle. This always works. You could find the last one by trigonometry, but it's longer. Why not? Why do you want to do trigonometry and just subtract, right? So find last angle by the sum of angles theorem, meaning complementary angles theorem. One angle is 90 minus the other in the right triangle. Okay, let's do one quick example of that. And it can work on the special triangles. It can also work on any triangle. Let's do this one. Just to do a quick one. Suppose I gave you a triangle that had these two sides now, 3 and 4. And I said, solve this one. What is that going to come out to be? You can probably get the first step right off, right? What do I do in the first step? Yeah, I call that C and call this beta, this alpha. So this is A and this is B. I'll say the third side by the Pythagorean theorem solve for C is square root of A squared plus B squared. Square root of 3 squared plus 4 squared is square root of 9 plus 16. The square root of 25 is 5, right? Oh, yeah, it's a 3, 4, 5 right triangle. And we'll pick an easy one so we do it quick. So you find the third side by Pythagorean theorem is the first thing you do. Now you find one angle by relating an angle to any of the sides you know. We could say, oh, let's do this one. So B, well, we know that the tangent of theta is equal to the opposite over the adjacent. That's our new definition, our right triangles theorem, is 3 over 4. The side opposite alpha is the one that doesn't help 4, the leg that doesn't help. The leg adjacent is the one that does help 4. So it's 3 to 4. All right. On the triangle, by the calculator, what you do is use the inverse function, say theta equals inverse tangent of 3/4. The inverse tangent is just above the tangent button. What you do is you push second tangent. We'll do more calculators next time. And the second button is like gold or blue. It's the same color as up here that says inverse tangent up here. It tells you the angle that has that tangent. And you just push 3 divided by 4. Some calculators want to close the parentheses. So this one, some calculators you don't need it. And then enter. Well, you're taking inverse tangent of 3 divided by 4. Those keystrokes will do it. We're over here. I was taking, like to do this, I was just taking cosine. I put the cosine button, 1, 0, close the parentheses and push enter. That takes the cosine of 10 degrees if it's in degrees mode. It automatically inserts the first parenthesis, and I insert the second parenthesis on some calculators. Some of it already inserts it. The calculator should say cosine of 10. Here it should say inverse tangent of 3/4. And we'll get when I do that. 6.86. Okay. I get theta equals 36.87. We'll round it. Degrees, since you're in degrees mode. You always wonder what the angle is in a 3, 4, 5 right triangle. There, what it is. There's what it is. It's not a pretty angle. But now, how do we get the last angle? It's really easy. Yeah, just subtract it from 90, and I shouldn't have called this theta. This is alpha. Alpha was angle. And so that was alpha. So now beta is 90 minus that number. Gives me what, 53.13 degrees. Now you can solve any right triangle given two sides or given an angle on a side. Real nice like that. This is a really important problem. Thank you so much for the calculator. What you can do for next time is look at 5.4. We haven't gotten to number 1 yet. That's the identity. Let's get that. Do 2 through stick. 5.4, do the stick, and finish all the problems. 5.2 and 5.3 now that we did all the identities. So these are all in the supplement. Finish 5.2, 5.3, the identities. Any of the problems you didn't do, and then 5.4 for the